Hi, I'm Leon Starr, and welcome to my course on how to specify software in complex safety-critical systems. In this lesson, we're going to see how we go about specifying and classifying all the things our software system interacts with. I highly recommend watching parts 1 and 2 of the course introduction if you haven't already, so that you understand why we place an emphasis on platform independence and executability throughout this lesson. Those principles shape all our specification and modeling techniques. Every software system interacts with things in its surrounding world. Many of these things are physical entities. In an air traffic control system, for example, the world might consist of various aircraft, radar equipment, beacons, runways, and such. I often describe these kinds of physical entities as things you can kick. There are also usually abstract entities in our system's world, such as landing patterns, flights, routes, waypoints. You can't kick or even see these things. Abstract things may be manifestations of policies, monitored activities, or managed transactions of some sort. Physical or abstract, our software system must monitor, manage, react, and just generally be aware of both kinds of things in the world it interacts with. I imagine you're familiar with classes in object-oriented programming languages like C++, Python, or Java, and no worries if you're not. Programming classes are fine when you're implementing a system. But our goal is to specify a system, so our objectives and definitions are going to be a bit different. When you implement, you're in a design mindset, and you need to create structures that are efficient and reusable, along with a variety of other coding considerations appropriate to a given platform. But when we specify, we're in an observation mindset. Our goal is to inventory, pick apart, and describe the things, behaviors, and rules in the world of our system. And the things we observe in our world must be recognized on all platforms. Let's say that we're specifying a system that tracks air traffic. We notice that there are all these planes flying around with certain properties. Each has a heading, an altitude, an airspeed, and so forth. Also, we observe that there is a rule which says that each of these things, let's give it a name, aircraft, has a unique call sign. Two aircraft might be at the same speed, but no two aircraft share the same call sign. We also note that these things all basically have the same behavior. An aircraft takes off from some airport, flies towards an intended destination, and then eventually lands, assuming all goes well, of course. To model this observation, we'll define a class named aircraft. But since we aren't creating a programming style class, what exactly are we defining? What we're actually doing is creating a set definition. You may recall from your old lessons in set theory that a set can be defined with some sort of rule. The rule can then be applied to determine which elements are included in or excluded from the set. For our purposes, we have a template for this rule where any candidate element in our set must 1. Have a certain set of characteristics, 2. Exhibit a certain behavior, and 3. Be bound by certain rules and constraints. To work out these criteria, we go back to the world of our system and observe. Observing some aircraft flying around, we note the common characteristics. It appears that each plane has a unique call sign, a current heading, altitude, and an airspeed. We also observe that all aircraft do pretty much the same thing. A given aircraft takes off from some airport, flies to some destination, and then lands and taxis at some airport. Finally, we note each aircraft must adhere to a number of rules or policies. For example, all aircraft must wait for clearance before taking off and landing. All aircraft must maintain a certain safe separation, and so forth. If we're happy with our classification, we can diagram it using standard UML notation. The top compartment has the class name, with the lower compartment giving us a list of attribute type pairs. Notice that we don't use implementation types like int, double, float, string, and so forth. We'll talk more about how we define types in another video. For now, just note that we keep everything platform independent. We also need to write up the reasoning behind our abstraction, including each attribute, type, as well as the class itself. If the behavior of our class is interesting enough, and in this case it probably is, we'll formalize it with a state machine. That special property of the ID attribute, where it's guaranteed to select a unique instance of aircraft, or none at all, is indicated with the UML tag there in brackets. Our methodology defines the I tag, short for identifier, to mark this constraint. In subsequent videos, we'll dive into all of these topics. For now, let's just focus on the class itself. Before moving on, let's do a quick aside about model descriptions. A lot of folks think of descriptions as some kind of tedious secondary documentation task. Ew. The real work is mousing around your canvas, drawing boxes and lines, right? And not so much. Imagine someone hands you a model diagram. Each item on that diagram reflects one or more decisions. These are the results of thoughtful analysis, trade-offs, consideration of nuances, choices about how terms are defined, and so forth. Each decision has a direct impact on the behavior and safety of the design software. The diagram tells you what modeling decisions were made and gives you something unambiguous to execute. But it doesn't tell you why any of those decisions were made. In the case of our simple aircraft class, we could ask, are balloons aircraft? What about helicopters? Why or why not? What does this aircraft abstraction really mean? Why do we need it? Why is the MSL, mean sea level altitude, expressed and not AGL, above ground level? Why call sign and not tail number? What's the difference anyway? Think of your graphics like a visual table of contents with all the hard thinking and problem solving in the underlying descriptions. By itself, a table of contents is nice, but rather difficult to evaluate and understand. In fact, much of the thinking that goes into building a solid model is the result of forcing yourself to write down your reasoning. The minute you do that, you quickly realize that there are lots of holes in your abstractions and missing information that you need to collect from the subject matter experts. This is hard work, but make no mistake, this is the work. Throughout this course, I'll explain and give examples of how to describe each model element. And we'll do this in a way that leads you to high-quality, problem-solving models, so that you actually feel that you're getting something real done and not just mired in a tedious documentation exercise. End of aside. The class notation represents a set definition. Any entities we observe at a given point in time that conform to this definition form a corresponding set of 0 or more elements. Here we have 3 such elements, each with its own set of attribute values. We refer to each element in our set as an instance of the aircraft class. Now this is a set, so no order is implied for either the instances or the attribute values. So we can move the instances around or shuffle the attributes in the class notation without changing our specification. A tabular representation tends to be a more convenient way of visualizing instance populations. Our attributes form the header row, and each body row represents an individual instance of aircraft. Column and row order are not significant, so we can move them around without changing the specification. Each attribute has an associated data type that defines the values that may be assigned in that column. We often use the word type instead of data type. Also, I often omit the type names from the table header to reduce clutter, but remember that each attribute always has a type. Since our set definition dictates commonality, there can't be anything special about any particular instance. Therefore, we should be able to reason and test the limitations of our class without looking at any particular set of instances. One way to do this is to see what questions our table can and cannot answer. Let's give it a try. Given some ID value, can we determine the heading of the corresponding aircraft? For example, if I ask for the heading of aircraft N12839D, can the table give me an answer? Yes or no? The answer is yes, absolutely. DCY. We can plug in the ID value and, if that instance exists, report the value in its heading column. Let's try another. Which aircraft are flying below, say, 5,000 meters? Can the table answer this? Well, yeah, it can. Just apply the predicate, altitude less than 5,000 meters, to each row and grab all the ID column values for all rows evaluating as true. Let's try a more interesting question. Is a collision likely in 5 minutes? What do you think? The answer is no, absolutely not. Our table is missing an essential attribute. You guessed it, position. It's going to be tough to write an algorithm to compute collision likelihood if you don't know where your aircraft are located. Now, if we add that attribute to our class, can we do it? We could, though you would be right to argue that even more information may be helpful, like the required separation distance between aircraft or the climb, descent, or turn rate. So with a single empty table, having only a handful of attributes, we're able to reason about our application requirements. Just imagine what we'll be able to do when we have a much larger number of classes and relationships. I hope you can appreciate how a more formal representation of the data forces us to think about the requirements in a bit more detail than a natural language statement. I wouldn't blame you for glossing over such a trivial example. Aircraft in a table, ho-hum. But we really did something pretty amazing just now that will yield massive benefits as we develop our systems analysis. One of the reasons why developers like to get right down to coding is so they can focus on something tangible, something they can perform operations on. Because when you start to actually build something that you're trying to get to work, you're forced to confront obstacles and limitations. But in most MBSE methodologies, you don't have that essential reality check. You can be content to draw some lines and boxes and call it a day. It is so easy to miss important details when the thing you're building doesn't have to execute. Notation on its own lets you get away with pretty much anything. But an underlying data structure with well-defined rules and operations keeps you honest and forces you to pay attention to the nuances of your subject. You can't just wave your hands when the going gets tough, claiming your models are high level in some sense, and leave the problem for the programmers or AI to sort out. This exercise, applied at scale, will blow holes in what may have appeared to be a complete specification, expose edge cases, and force you to realize that you know a lot less about your subject than you thought you did. This may not sound like much fun, but it's a lot cheaper to have these realizations occur early in your specification process and not have them surprise you after a misinformed design has crystallized. Obsession with notation rather than testable, executable semantics is one reason, in my opinion, that many software modeling methods have failed to deliver value. You might be wondering at this point, are tables really a platform-neutral data structure? We're claiming to build platform-independent models, after all. Also, how exactly do you make a class executable? What specific operations can you perform on a table? And finally, what are the design implications of specifying real-world or abstract entities as classes in the first place? Aren't we biasing our specification toward object-oriented implementations? I will tackle all of these questions and more in our next video, Executable Classes.